Hi class, welcome to our Grad Stats 2024 Lab Series. In Lab 4 in SPSS, we're doing multiple and hierarchical regressions, and we're going to deep dive into our model level assumptions. So again, multiple regression is this statistical analysis technique that's built from correlation, but gives us the ability to look at relationships between multiple variables, which is a little more realistic to the types of questions we have in real-world organizations in practices. In this lab, we're going to conduct and interpret a multiple regression, a hierarchical regression, and we're going to evaluate the quality of those models using the model level assumption checks. Materials you're going to need are the dataset survey.sav from Pallant's SPSS survival guide, the Lab4 Labsheet, and the starter tables Excel. So download those items, get them placed where you need them, and we will get started. Starting with our data set here, you want to open the survey.sav data set, and this is the one that already has these totals computed for us. So make sure that's the one you're opening up, and also have your lab sheet on the ready. It goes over the purpose, the goals and skills that we're going to be working on in this lab, and it sets us up with these research questions that are relevant for regressions. Research question 1 says, how well do two predictors perceive control of external events, which is total mastery, and perceive control of internal states, which is our PCOS scale, predict the outcome of perceived stress, TP stress? And then, so that's your multiple regression. Then our hierarchical regression is what applies to research question 2. If we control for the possible effects due to age and social desirability responding, is this set of predictors, TMAST and TP-COAS, still able to predict the variation in perceived stress? And this is very applicable to the things that we are looking at in practice. Because age and social desirable responding are things that we cannot control, not as an organization or not as a researcher. So we want to find out and kind of pull away the variation that's already being explained due to someone's age or their social desirable responding, and then see out of the variation that's left to explain, are these predictors of total mastery and total perception of control of internal states, are those two still able to predict a significant amount of variation going on in that outcome of total perceived stress? So that's kind of where we're going with those questions and the analysis that we're using to answer those questions. Of course, you already have your files, and our preliminary look is to, again, read in that data set, make sure that we've taken care of anything that needs to be recoded. Like you could add your labels, you can make sure that everything is correct according to the code book. Typically, this being the final data set, everything's pretty much set. When we're talking to our reader, we want to give them that general description of the data set and the variables of interest. So what we're looking at there is those specific predictors and outcome. We want to be able to describe those to the reader in terms of mean and standard deviation, but we also need to know how many sample actually have values on those predictors and outcome. So you would still do your univariate normality assumption check of both the predictor and the criterion variables, and you look at the bivariate linearity between each predictor criterion pair. So let's take a look at this real quick. In our data set, we need the descriptives. So I'm going to go to Analyze, Descriptive Statistics, Descriptives, and I want those three, T-Mastery, total perception of internal states, and total perception of stress. I want to have at least those to know what's going on with them. So I can paste that into my syntax window and be able to take a look at what's going on. So here, descriptives of these variables, I want mean, standard deviation, min, and max. And you can even put in like your skewness and kurtosis and go ahead and start doing your univariate normality here. But I'm going to go ahead and run this so that we can get a look here at these variables. So we got mean and standard deviation for total mastery, total perception of internal states, and total perception of stress. We also see here in the valid in 426 cases have values on all of those variables. So that's something we're going to need to know later on when we're trying to find information about the model. So it's good to have that. But again, you would go ahead and do your preliminary checks like your univariate normality, bivariate linearity in preparation for a regression. I'm just skipping it here because we've already done that in a prior lab and I wanted to save time. So going back to our multiple regression here, we want to do analyze regression linear and follow these steps. So let's do that. I want to analyze regression linear. I want total perceived stress in the dependent, because that's the outcome we're interested in. And then the predictors are total mastery and total perceived control of internal states. So we'll put those in the block 1 of 1 area. And then in options, we're going to want to make sure it says exclude cases listwise. So continuing there, and here we are ready to paste. So now we have in our syntax the regression command. Leave myself a note, that way if I come to the syntax later, I know what I was doing. We have calling for a regression. It's going to leave out any cases that don't have values on all of those variables. Which variables? The dependent of total perceived stress and the predictors of T-mast and T-PCOS. So running this, now we have some information. In our output here, we have model information and predictor or coefficients information. And you're kind of telling the reader about the big picture first. Is the model significant? And how much effect does the model have? And then you go into the details on what is the contribution from each of these predictors in the regression coefficient. So we can see the model is significant. In other words, this regression model significantly predicts variation in total perceived stress. The information you would need for your stats line is the F estimate, 184.49, and the degrees of freedom, 2 and 423, that it's significant at p less than 0.001, and then you want your effect size, the R squared, in the model summary box, 466, and that's telling us that when we convert that to a percentage, that 46.6% of the variation in total perceived stress is explained by this model, the whole model. Now, the information we don't have in SPSS when we're talking about the model is the confidence interval for this R squared. For that, we got to go back to that Daniel Soper website and scroll down to regression. and look for the regression coefficient. Nope. R-squared confidence interval calculator. That's the one you want. And in here, we need to give some information. How many predictors? 2. We had total mastery and total perceptions of perceived control. And then the observed R-squared, that's the one in our output, the 0.466. And then the sample size. This is why we needed to find out how many cases had values on all of these variables. And the answer is 426. Calculating there. And we have our 95 confidence interval right there. So that's the information we're going to need to complete the write-up of the model. We still need to give our reader information about the coefficients. And that's going to be in this coefficients table. So here, just looking across for total mastery, we see that it's significant. It's a significant predictor at p less than 0.001. We see that the unstandardized regression coefficient of negative 0.621, that's telling us that for every 1 unit increase in mastery, there's a decrease of 0.621 in total perceived stress. So the higher someone perceives that they have control over external events, the reduced perceived stress is predicted. We also have the beta, which is the standardized coefficient, and it's also the effect size of that predictor. So it's effect size of the contribution of total mastery to this model. And then for total perception of control, we have an unstandardized negative 0.175. For every 1 unit increase in the predictor, total perceived control, there's a reduction in the outcome of 0.175. So that's the trick of it. You got to remember which one's getting the 1 unit increase, because these numbers pertain to the outcome, total perceived stress. And again, the standardized coefficient, beta, is the effect size and the significance value. So let's talk about standardized coefficient for a second. It's the effect size relative to the other predictors in the model. So it doesn't always work out the same. You see how these numbers are different. And what's going on is relative to each other, it turns out that mastery is a little stronger than total perceived control of internal states, because negative 0.42 is more impact on total perceived stress than negative 0.3536. So we're able to look at this model and not only see that the predictors are significant, but then when it comes down to it, perceptions of external events, control of external events, total mastery, is a stronger predictor of reduced stress than total perception of internal states, according to this model. So that's information we can use to translate the information we're getting in the output to our reader or our client or our organization. So let's take a look at, this is just the same information on our that we got in the output. And here's what our interpretation or our write-up might have in it. We need to let the reader know that the model is significant, and we give that information about it's an F-test. What is the degrees of freedom? What was it estimated as? What was the significance value? What was the R squared? And what was the 95% confidence interval of R squared? Then we go into the specifics about the coefficients. We let the reader know that the coefficients indicated that total mastery and total perceived control were significant predictors. One way or another, we want to let the reader know that. And our stats lines for those coefficients are going to be the unstandardized value, the significance level, and the standardized beta value for that estimated regression coefficient. So you're letting your reader know both of those. You can have an interpretive statement letting the reader know what's going on, what is the change in perceived stress for every 1 unit increase in these predictors. And then it's the beta that we use to let the reader know which predictor was stronger. So that's how we help go from the output into the write-up and communication. Okay, we're going to move forward here, and we'll go back and run that linear regression, but now we're going to put some extra things in there so that we can evaluate the model level assumptions for this particular model. So analyze, regression, linear. Again, we want our total perceived stress and our two predictors, total mastery and total perception of control. And the options again being making sure that exclude cases listwise is indicated. Okay, we're going to add some more things in here. In the statistics tab, I want you to grab, make sure model fit is selected. And here down in the residuals area, you want case-wise diagnostics. And it should already want outliers outside of 3 standard deviations. That's cool. And then we're going to go to the plots section. And here, down in the standardized residual plots, select both the histogram and the normal probability plots. And we're good there. In the save area, we're going to want the predicted unstandardized and the residuals unstandardized and the cooks in the distances area. Continue there. And in options, we want to make sure that it's exclude cases listwise. Okay, once these are all ready, we're ready to paste to syntax. All right, let's take a look at this. Especially note the differences between the straight multiple regression and the multiple regression with the extras included. So some things are the same, right? The differences is when we asked for the histogram and the probability plots. We got the case-wise when there are outliers more than 3 standard deviations, and we saved some extra variables going on here. So we're going to have new variables in our data set as well. So running this guy, let's take a look. First, let's consider that the assumptions at model level are mostly about the residuals. And what are we talking about with the residuals? I'm going to go over to our data window here, specifically our new variables that we have. And let me drag down total perceived stress to where we have it with the others. And then we'll go look at that. So the predicted value for total perceived stress, the residuals, and what total perceived stress actually was. So this is measured from the participant, and based on the data, and the model estimation, this is what we predicted it to be. And the difference between those two is the residual. Like we can even check it out with a calculator here. If we take what it was, 29, minus what we predicted, 28.26128 equals 73872, which is the residual, right? That's all a residual is the amount that's different between the predicted value and what it actually was. So these residuals, we're looking for them to have specific characteristics, and that's what we're checking mostly when we're talking about model level residuals. So let's check some different things. First, we'll talk about something that's not directly residuals, multicollinearity. And this refers to when our predictors are too highly correlated. Now, typically you would have already run correlations between the study variables earlier when you did preliminary bivariate linearity checking. But let's go ahead and check it here. Correlating between the two predictors. So I want to know between total mastery and total perceptions of internal control. So I'm going to paste that and go over to my syntax so that I can run it. There we go. And I can even give myself a note here. Checking multicollinearity. So when I run this, I see that they are significantly related to each other at 0.521, which is a good strong correlation, but what is too high? Too high is 0.9, either positive or negative, doesn't matter. So we are not up to 0.9 between our two predictors. So we don't have to worry about multicollinearity here. So that's one check. Another check is called singularity. I'm going to go back to our variable view. And singularity has to do with, are we counting things twice? Like, remember when we were creating scale level scores, all of these items go into the total scores. So if I have something like mastery and I'm looking at mast 1 through 7 that goes into the scale level score of total mastery, I wouldn't want to have the items and total mastery in the equation at the same time, because then I would be counting those items twice, once as items and once that they're in the scale level score. Similarly, if there were items that went into mastery that also go into total perception of control of internal states, that would be a problem with singularity. That item, if it was in both of those, would also be counted more than once, and that's a violation of singularity. So it's not something we really test for, but it's something that you want to know about your data. If you know you're creating different composite variables and some items going into the composite variable that you're using are also being used in a different way in the model, then you know you have a singularity issue, a violation of singularity. So after that, let's talk about outliers. And again, outliers are those very either very high or very low scores. And for this, we're going to come to our output that was provided, specifically the case-wise diagnostics and in here in the residual statistics. So remember we asked for, is there anything more than 3 standard deviations, any residuals that are more than 3 standard deviations away. So it looks like case number 55 has a standardized residual of -3.471. That's telling us that that's more than 3 standard deviations away from what we would have expected. So for that case, case 55, we did a really horrible job of predicting what their total stress would be. And then another way, so it's something you might want to say in our write-up, that we did identify a case that was more than 3 standard deviations away. It's residual. Another thing you check there is Cook's distance. So down here in our residual statistics, Cook's distance says the largest value it had was 0.096. And our cutoffs for Cook's distance is 1, plus or minus 1. And we see that there were no cases with a greater Cook's distance than 1. And another way we can look at this, if we go to our data and we double click to get our Cook's distance there on data view, we can sort this descending. So I right click the column and I put sort descending so that it puts that biggest one up top. So this is the one that could be considered the outlier. On one hand, it's more than 3 standard deviations away in its residuals, but on the other hand, its Cook's distance is not exceeding the cutoff. So you can tell your reader, like, a case was identified as being an outlier, however, the Cook's distance did not exceed the cutoff of 1. So you can go either way with that. Usually when you find an outlier, you first try to find out if there's an error in the data entry, just in case it was a data entry error, or you see if this particular outlier is impacting the analysis. This one is not likely to impact the analysis because this distance is not anywhere near 1. So, but we do want to let our reader know about it. And then the next 3 items, the normality, linearity, and homoscedasticity of the residuals, is looking at those characteristics of the residuals. So let's take normality. Normality is simply, are the residuals normally distributed? And recall when we were looking at univariate normality, we're looking at a couple of things to evaluate that, right? We're looking at the histogram of the variable and the Shapiro-Wilks test, right? So what we're going to do to look at normal distribution of the residual, we're going to look at its histogram. So here is the standardized residual, and these were from the plots that we asked for. So we have a nice histogram of standardized residual, and it's got a normal curve overlay on it, so we can do a visual inspection of this histogram. How much does it match to a normal distribution? So this is a graph that maybe you want to keep for a write-up, or it helps you tell the reader the normal distribution of residuals for this model. Another graph we're looking at is the normal PP plot. And again, this is that diagonal line is what we would have expected the values to come in at, and the dots are the actual values. So how well our dots line up on the line is an indication of normal distribution of the residuals. Let's go on to linearity. Linearity of residuals is saying that we want no linear relationship between the residuals and the predicted values. So when we're talking about that relationship between variables or between things, we're talking correlation, right? And when we were looking at bivariate linearity, we were looking at a scatter plot and the correlation test, right? Same idea here. We're expecting that there is no relationship between the residuals and the predicted values. So 2 things. And it happens to be 2 things that we have when we saved the predicted and the residuals here. So we have those two variables. We just need to look at a scatter plot and look at the correlation test between these two items, these two variables. So back to our scatter plot. Go to Graphs, Chart Builder. We need a scatter plot. Drag that in there. Let's put the residuals on the y-axis and the predictor on the x-axis. Hit OK, and let's take a look at this guy. So here's my scatter plot between the predicted values and the unstandardized residuals. And what we're looking for is there a linear trend going on here? Do we see the relationship being positive or negative? And I'm not seeing anything there. So that's good, because we don't want a relationship between the predicted values and the residual values. Okay, and then the other thing we can check in terms of linearity, going back to that, is the correlation between these two. And that's just like the correlations we've run before. We go to Analyze, Correlate by Variate. I'm going to reset this, because now I want these two, the predicted and the residual, over here to see their correlation. So I'll paste and go to my syntax. Give myself a little note so I know what it is later, and run that guy. So the correlation between the two is 0. That's pretty solid, no relationship there. That's good, because that's what we want in terms of seeing if linearity of the residuals was violated. Here we have a non-significant test, so that means we're good. There's no relationship between those two. Next, we're also going to use this graph to look at homoscedasticity. And that is saying that the residuals are distributed similarly across all these values of the predicted value. So what we can do is add a reference line to the y-axis at 0. And we can also make it a color or make it stand out, make it thicker so you can see it. Applying that and closing and closing. So now I can see the distribution of these predicted values across different residuals. So I'm looking at the spread both above and below the 0 line, and I'm looking at the spread of residuals on this value, this predicted value, 20, compared to this predicted value of 40. So you're looking at, it should pretty much be like a block or kind of circle-y shaped, and we're getting a pretty good spread there. It's not looking like a funnel, like really skinny at one end and wide on the other end. So looks okay on homoscedasticity here. Okay, those are the assumption checks that are easily accessible here in SPSS. And now we want to see, how does this look in a write-up? As before, we let the reader know what we're up to, what kind of regression or what kind of test is being done, and between what variables. So I started with a multiple regression was conducted to evaluate if perceived control of external events, T-MAST, and perceived control of internal states, TP-COAS, predicted perceived stress. Assumptions related to multiple linear regression included multicollinearity, which was evaluated by looking at those, are the predictors correlated? And usually you're doing that during the first part of your preliminary look around. Assumptions evaluated through examination of residuals included looking for outliers and the regression diagnostics of residuals, and in terms of normality, linearity, and homoscedasticity. We did find an outlier case, but Cook's distance was less than 1, so the case didn't seem to have an extremely divergent influence on the trend of data. When we look at the scatter plot between predicted and residual values, we see that there's not a whole lot of relationship there, and it was confirmed with our correlation test. We also looked at normality of residuals by looking at the normal QQ plot and also the histogram of the residuals. Again, the scatter plot between residuals and predicted values showed no trends, and looks like we've met the assumptions of normality, linearity, and homoscedasticity. So that whole paragraph, most of it, was just about assumption checking, right? And then I put that ahead of giving the reader the results of the multiple regression, that they were significant. There's my F line. All of it, like we did before, the 46.6% of the variation. So that's back to the regression that we ran in the first place, but I put all the information about checking the assumptions before I gave the reader the results of that model and the coefficients of that model. The last thing here, writing your prediction equation. The way you do that is you look back at your coefficients table. So I'm going to scroll back up to there. Yep, right there. So in your coefficients table, you have the constant, which is also called the intercept, and you have the impact of mastery and the impact of perceived control of internal. Those are the numbers you're looking to use in your prediction equation. So there's our constant or intercept. Here's the impact of mastery, so negative 0.62. And we put a leading 0 because regression weights can be above 1. Whereas when you have a number that can't go above 1, you don't include the 0. Like for, if we have right here, the multiple r squared, it can't go above 1 anyway, so it doesn't get a leading 0, whereas our regression weights can be above 1. We have the figures. On these, I labeled a few of the outliers. We have the QQ plot, and this is a good point for a break. If you want to shake it off, go get a cookie or a drink or something, this is a good place for it, because the next thing we're going to go into is hierarchical regression. With hierarchical regression, we're looking at controlling certain variables before we look at our target variables. In other words, can we find out the effects that are due to age and socially desirable responding on total perceived stress, and set that aside, take out that variation, and then see if our predictors of mastery and perceptions of control still are able to predict a significant amount of variation in perceived stress. So our model gets a little more complicated, but at this one, we're going to request assumption check information at the same time that we are calling the regression. So it makes it shorter because we're asking for all the information up front. We want to go to Analyze, Regression, Linear. And here, I'm going to take out mastery and total perceived control of stress. I still have the total perception of stress in the dependent area, but now in this block 1 area, it might also say independent, but this area here, we want those 2 step 1 items, age and social desirability, which is the T Marlowe. So those are in block 1 of 1, or it might say independence. Then we want the next button. When you hit next, now you have block 2 of 2. And this is where we want our main predictors, or predictors of interest, T-MAST and T-PCOS, right there. We keep most of the other things the same, like our statistics, that we have regression coefficients, model fit. We are asking for case-wide diagnostics. We can get the confidence intervals for the regression coefficients. That's another way of telling the reader about the coefficients. So you can include that, or you can also just report your beta as your effect size for those. We want here R squared change, because we're actually running 2 models and looking at the change in R squared between those 2 models. And that looks good there. In the plots section, we want the histogram and the normal probability plot. And then in save, we're going to have the unstandardized predicted, unstandardized residuals, the Cook's D, and go ahead and get the standardized residuals as well. Hit continue here. Options, we want to make sure that it's excluding cases listwise. And I think that is it. We'll hit paste and be able to label our syntax. Running this one. Now we have all of that information again. So taking it step by step is what you want to do here. You can tell the reader just about the model and the regression coefficients. Let's say, and when you're looking at your model, you're looking at model 2 mostly, that had all of the variables in it. For example, on model 2 here in your coefficients table, it had age and T-Marlow and T-MAST and T-PCOS. Here in the ANOVA table on model 2, we have our F stat. We have that it was degrees of freedom 4 and 418, and it was a significant model. Now the model with just age and T-Marlow was also significant, and it's got its own stats line. And up in here in model summary, we have the R squared, that the effect size of model 2 that had all of the variables in it was 0.470. That model explained 47.0% of the variation in the outcome, total perceived stress. And then here, F change. This is our partial F test right here. That the change from model 1 to model 2 had a significant change. Like there's our significance value for this partial F test. The partial F test has estimated value, degrees of freedom, and that it was its significance. And here's our R squared change. The additional variance explained went from 5.9% to 41.1% between model 1 and model 2. So that's a lot of information, right? Model 1 had only age and T-Marlow, and model 2 had all of them, and we have multiple F lines here. We have the F line for model 1, we have the F line for model 2, and we have the partial F line telling us about the change from model 1 to model 2. So that's a lot of information about the model. When we get into the coefficients, we're mostly reporting just from the model 2. That once we controlled for age and social desirability, this is the impact of these predictors, these main predictors we were interested in, total mastery and total perception of control. So both of them still stay significant predictors even while controlling for age and social desirability. And here are all of the unstandardized coefficients for them, as well as the standardized coefficients. So that's the information we need for writing up about the hierarchical model. Let's take a look at that real quick. So here's areas where I've circled the information that we're pulling mostly from, and the coefficients being in Model 2. But let's take a look at this right up here. This first paragraph is about checking the assumptions of the model, so we'll come back to this. Let's start down here in this paragraph. We let the reader know in this hierarchical model that age and social desirability were entered at step 1, and with that it explained 5.7% of the variation in perceived stress. Where was that at? Right here. And I must have had a different setting somewhere, but 5.9, 5.7, that's where that number is coming from. After entry of total mastery and perceived control at step 2, the total variation explained in the model as a whole was 47%. So there's that 47.0 right there for Model 2. So that's the whole Model 2 with everybody there. And there's our F line for Model 2, right? So 418, 9267, significant. And we have 418, 9267 was significant with this R square. That's where we're getting the information for that stats line right there. And again, we have to go to Daniel Soper to get the 95% confidence interval for Model 2. Going into more detail here, the two measures explained an additional 41.3% of variation in stress after controlling for age and social desirable responding. So where is that 41.3% at? That is our right here, R square change. So there's probably a little bit of difference from when I ran it first to run it now, but here 41.1%. And we can fix those. 59 and 41.1, so 5.9, and this guy 4.11, so that it matches. But you can see that up here, when I ran it before, it was the 59 and the, oh, it's still 41.1. I must have had that wrong someplace. But cool, good, get that corrected. After controlling, so that's the partial F test right here. F2, 418, 162, significant, and the R squared change. So that delta means that it's a change in R squared, what the delta stands for. So this stats information is in up here, our partial F test. So our F 162.07, degrees of freedom 2 and 418, and our R squared change. That's what we're seeing right there. Now we're going in, like right here at this sentence is where we're getting into more detail about our focal predictors themselves. Both of them were still statistically significant after we had already controlled for age and social desirability. And then here's our stats line for total mastery, which we have right here. Total mastery, -6.3 and -4.3. -6.3, -4.3. And higher effect size than perceived control. There's perceived control with -16 and -33. So -16 and -33. And you see that I worked in the information about total mastery had a higher effect size, and that's based on the beta. Beta is comparing within relative to the other predictors in the model. The beta tells you who has the higher impact. And then our prediction equation now has all of those items that are in model 2. So the constant or intercept, the regression estimate for age, the regression estimate for social desirability, the regression estimate for mastery, and the regression estimate for PCOS. Wow, a lot, right? So before we go into tables and stuff, let's step back and check out the information for the assumption checks of this model. So then all of those things, those extras we asked for, we have that information here. So we have a case that was greater than 3 standard deviations. So that means there could be an outlier there. But when we come down to Cook's distance, it looks like the maximum was 0.059, nowhere near a 1, so probably not going to worry about an outlier here. So that's outliers. Multicollinearity, again, you're looking at, are your predictors highly correlated? So we can bring in a correlation of all of our items. I'm going to reset this, and we had age, social desirability, and mastery, and TPCOS right there. So paste and running this one. So I'm looking for any correlations above 9, above 0.9. And again, we only have to look at half of this triangle because it just repeats. And it looks like no matter what, we don't have any correlations above 0.9. So we don't have a concern with multicollinearity here. So that's good. The other items, outliers, we already looked at that. Normality, linearity, and homoscedasticity of the residuals. Again, we're going to look at the normal PP plot and the histogram here for normality. Here's our histogram of the model, like not of a specific variable in the model. This is the residuals that were created through the estimation of the entire model with all of the predictors in there. So there's our look, our visual inspection of the histogram for the residuals, as well as the normal PP plot. How well do you feel those expected residuals are lining up on the line? And then linearity, scatter plot between predicted and residuals. So going to our graphs, chart builder, and now we're going to reset this so it doesn't have the old ones in there. We'll get scatter plot again. And see how now we have 2s? That's for, because we asked for it again. The only one that's a 1 is the standardized residuals, which this is the first time we asked for that, is why it's a 1. But it's still all about the hierarchical regression. It's just the first time we asked for it. So we want the residuals on the y-axis, the predicted on the x-axis, and let's go take a look at that. Again, not looking like a whole lot of relationship there. And we can ask for the correlation between those two. I'm going to clear this with the reset and go down to the bottom where I have predicted and residuals, and hit OK so that I can see. Looks like it's got a 0 Pearson correlation between the predicted and the residuals. Good. That means I have not violated linearity of the residuals. Next, the homoscedasticity of the residuals. I'll put myself the little Y line at 0 so I can take a look. And that might be a good graph to have in my write-up there. And it looks like we have just the same kind of spread going on all over the place. I'm not seeing like a funnel shape or more at one end than the other. It looks fine homoscedasticity-wise of the residuals. So one question here is, why did I ask for the standardized residuals? This guy right here. One thing you can do with checking for outliers, because see, now we have standardized residual and we have Cook's distance, and these are about the same model, model 2, or the hierarchical model. When I look at these, and we can, in our case-wise diagnostics here, we know that there's a potential outlier with more than 3 standard deviations, right? And it's -3,449. When we sort the standardized residuals here, that we sorted descending, and here is a positive 2.89. So positive 2 is not greater than 3. The issue with our standardized residuals is that right here, any that are greater than 3, but it could be -3 or positive 3, right? Here's the positive end of our standardized residuals, but they don't exceed 3. So I'm going to sort again, and this time make it ascending so that my lowest numbers are at the top. And here is that one guy, the 3.44889, that we're seeing in the case-wise diagnostics there. And the reason I wanted to pull standardized residual for you on this one is to be able to see this relationship here. That case that could be an outlier, the -3.44889, is also the one with the highest Cook's value, the 0.0588. So our highest Cook's value over here, the 0.059, it's the same case. So we can look at that one and say, hey, this particular case here could be an outlier. It's ID number 459, but sometimes when SPSS runs it, it gives it its own case numbers. But this way we were able to identify exactly which participant had the high standardized residual, greater than 3 standard deviations on that standardized residual. But we know that it's also this one with the Cook's distance that's not really exceeding 1, which is the cutoff for Cook's. So either way, you can tell your reader, hey, we identified an outlier that's more than 3 standard deviations away with its standardized residual, even though the Cook's distance was under 1, was within cutoff. And you can say, we still think it's an outlier. Or you could say it the other way. Hey, we identified a potential outlier due to the standardized residual being more than 3 standard deviations. However, with the Cook's distance less than 0.1, we're not considering it an outlier. Either way, just give your reader the information. They can decide for themselves if that one participant was an outlier or not. Okay? Alrighty, what's the other thing? Homoscedasticity. We're good with all of that. What we need to do now is build that regression table. So for that, we're going to need our information here from our hierarchical regression, and we need that starter table that we got. So in our starter tables, again, you have all kinds of different tables here that we're going to be working with. And we're going to move to Table Regression 2, which has a template for a hierarchical regression. Now, this one that's on your template has 3 steps, and we did not do 3 steps in the lab. Likely you're going to have 3 steps in the homework, so it's something you want to keep in mind here. So I don't need step 3 because we actually added both age and social desirability and mastery in psychosis all in step 2. So what I can do here is just do step 2. I don't need all of these, so I'm going to delete. So now I have step 1, step 2, and all of this information I can get out of the output, but I need to clear out what I have here so that I can make sure I have new information and not getting lost, right? And for ours, we didn't ask for confidence interval for the regression coefficient, but you could. You can leave it there and fill those in, or if you just got beta, which that's that one where it's a Greek letter, that's our standardized coefficient. That is what we made sure we had on each of these. So if you want to take out those 2, you can. And now I just have these. I'm not sure why I have an extra variable one there. I'm going to take out that row. Okay, that's the information I'm pulling together for this hierarchical regression. Let's see I want to keep my output, but have this, so. Okay, so step 1 is the model 1 here. I had a constant was 31 to 40. I can even add that in. Let me insert a row. I can put constant. Can do that on here too. And it's also called intercept, so either one is fine. The constant was 3124. So I'm just going to fill in all this. I'll speed it up so you guys can just watch it go. Okay, so I'm going to at least make sure it rounds to 2 places for anything that's a number. And I did round everything to 2 places, I think, most of the time. Looks like I need to fix that one. So anything that I put a apostrophe in front of, the Excel does not recognize it as a number. So I have to remember that. Center everything. I'm going to make sure everything is to the top. And that looks like everything I need for crossing this to my Word document. So I'm going to select all of that and then go over to the Word document. I already had a table from doing this before, but I'm going to take out that one. So that I can paste the new one and just work from that. So again, it looks like I have a margin issue over here. So I'm going to select the whole table, go to Layout, and Auto Fit to Window. Okay, that seemed to work out okay. I see a problem here with my beta being down a line and having its own like table within. So I'm going to try to fix that. I'm just going to delete that little bitty table with the beta in it. Okay, so I have some fixing to do there, right? I'm going to turn on these so that I can see what's going on. Like I see a return there that doesn't need to be there. So I hit delete to delete that extra return. And I'm going to want this line on the bottom too. And make sure everything's like top aligned here. Looks like it, but I'm wondering about that. So I'm going to do a bottom border there. It changed it. You can see how it's thinner. And I can do a top border. Yep. Okay, that'll work. But I need my beta back, right? What I'm going to do, because I think it was just adding a lot of space on that Greek letter beta in Excel when I was crossing it over to Word. So what I'm going to do is find beta in Word and then copy it into there where I need it anyway. So I'm outside of the table here. I'm going to go to Insert and Equation. And in here, I get to find beta. There it is. So now that it's right there, I'm going to just select it. I select and copied. I'm going to come up to here and paste and see if that'll work. Oh, not bad. Now the return is after the beta instead of in front of it. So all I have to do is hit delete once. Let me see if I can just get this sucker to go centered. Okay, cool. That worked. So it's a little bit of fight with the table sometimes, especially when we have more interesting symbols and stuff. Sometimes you also want to let the reader know what that is. Like, I don't have confidence intervals here, so I'm going to take that out of the note. But I might want to tell the reader that this equals standardized regression coefficient, period. That should not all be italicized there, so I'm going to turn that off. Cool. So I've let the reader know what the that the standardized regression coefficient is the beta. I can let them know that the B, the normal B, well, it is italicized, so B equals unstandardized. Now, typically your reader is going to know that already, but what APA likes us to do is anything that is abbreviated in the table, we want to go ahead and tell the reader what it is. Okay, we still need to apply the asterisks, right? So I'm going to go back to my output here and look at that here, age, T Marlowe, T Mast, and T Picous. Out of those, only Mast and T Picous are significant, but they're to the P less than 001, right? So I'll come in here and put the asterisks. And so far I only have those, but let's go up and see model 1 here. Age is not significant with a 134, but T Marlowe is at 001. So again, back to my social desirability, 1, 2, 3 for that one. And I don't have any p less than 0.5 or p less than 0.1, so I can go ahead and take those two out of the note because they don't apply. They don't apply to this table. So here I'm going to turn off the the non-printing characters so it looks cleaner, and that way I can take a look at it. Like, okay, am I missing anything? Looks like was this a 1 before? I don't remember typing a 1. Oh, it rounds to 1. So that is legit. Okay. It does round to 1. All of my numbers are good. Okay. And I don't need that guy there anymore now that I copied it and put it where I needed it. Okay. That's our table. It's going to be table 1 since it's the only table we gave the reader. And then in our information here, we would let the reader know some place in here where the table is. I think I'll put it right at the end of that first sentence. Right there. Okay. And then the figures that I selected these for the assumptions. And then again, your figures and tables go on separate pages. Here's my figure 1. And here's my figure 2. And in the homework, I ask you for 3 figures, so you'll need to decide what figures you're going to use. Okay, this looks like all we have for our lab number 4 in SPSS, and we did a lot. We conducted a multiple regression and looked at the assumptions the first time just for that regular multiple regression, right? But then we conducted a hierarchical regression, which is kind of like a more complex multiple regression, to see if we had a significant increase in variance explained when we controlled for age and social desirability in the step 1, and then looked at our focal predictors in step 2. And then we had to bring all that information out of the output into our write-up, which it takes quite a doing, right? And we also built a table and selected graphics for helping convey the information about the hierarchical regression to our reader. So lots to do there. You definitely deserve a cookie. So loved hanging out with you in this lab, and I'll see you in the next lab.